Okay, let me get my markers prepped. So I'm going to keep talking a little bit about angular momentum today, just to give us an idea of quantum mechanics and spinning things a bit. We'll kind of take a break on Wednesday. I showed a video on Thursday in class, and I think I'll show it to you guys just to be fair. A little bit of a diversion. On Thursday, I showed a lecture from like 1964. It was an old lecture from a Nobel Prize laureate named Richard Feynman. He's a scientist from Queens, got a very thick Queens accent. Won the Nobel Prize for the physics of the electron and the photon, relativistic theory, so the electron moving at the speed of light, or near the speed of light. What they call quantum electrodynamics. He's a really famous physicist from America. His big kind of, most people know him for, he was the head of the Challenger investigation committee when the Space Shuttle Challenger exploded in 1986. He was the head of that investigative committee. That was kind of the twilight of his career. But he's quite famous for his teaching and his books, his textbooks on physics. He gives a really nice lecture for a general audience about the double slit experiment, about the idea that a concept in quantum mechanics that we can't know everything all at once. That we can know, as we'll learn, you can understand something's position, but you can't understand its momentum. Maybe the homework actually kind of talks about this idea of the uncertainty principle. And I think he gives a very clear explanation of it. It's kind of, well, I thought it was funny. The rest of the students didn't think it was funny, but it's not exactly Gen Z humor for sure. But he's got a nice tone, a nice characteristic, and explains it very well in kind of a nice casual way. So I think I'll show that to you guys on Wednesday. I think it'll help clarify some of the confusions. But you'll learn that it doesn't actually clear any confusions. You just realize that everyone is equally as confused as you are about quantum mechanics, and that's just a part of reality. He even says that even he still doesn't understand quantum mechanics. And of course the man's won a Nobel Prize for it. So, and I still struggle with it on a daily basis. So I think he teaches that idea very well. But I first want to talk a little bit more about spinning things today, just to get us at a good stopping point, and then we can kind of take a break. Eventually we're going to want to talk about many different types of spinning things. We're talking today. What I introduced last class was just taking a diatomic molecule, for instance HCl, right? And we're just going to give it some angular momentum at some angular frequency. We can define a center of mass here, right? And it's actually the center, the thing spinning around the center of mass. We'll say they're moving clockwise, counterclockwise, this way, rotating this way, at some angular frequency, omega. That's how fast it subtends a radian per second, how many radians per second it's rotating. Eventually, we're gonna want to think about how universal this theory is. We're gonna do the exact same process with this, right? We're gonna have this diatomic molecule. We're gonna calculate the energies of its rotations, its angular momentum, come up with a wave function, calculate energies. We're gonna do the same thing we did for the particle in the box, but now we're doing it for a rotating system. And what we're gonna have to learn how to do angular momentum math, if you will, and calculations. Physics of angular momentum, and what we're going to find is that those are essential for chemistry. In fact, they're even more fundamental than just this, right? We're going to end up thinking about, remember that the hydrogen is a proton plus an electron, and this electron is spin 1/2, and this proton is spin 1/2. We've talked kind of briefly about these ideas of spin, but in fact, spin is just angular momentum. Every component, every system that has a spin that's not zero has some intrinsic angular momentum about it. Right? That's what spin is. It's almost as if the electron is a top, and that constantly spins. And so if you think about the electron this is a really bad way to think of the electron, but if you think about it as something that, like a spinning top that spins around this axis, there are two ways that it can spin. One is it can spin with the angular momentum pointing in this direction, and the angular frequency of this is 1/2 h bar. And then there's an equivalent way, we'll call that L plus if you will, there's an equivalent way for the electron to also spin, which is in the opposite direction. We'll call that L minus, and the omega is minus 1/2 h bar, if you will. And every particle has this, right? If it has a spin of, it's not 0, for instance, an electron is 1/2, or a nitrogen atom is 1, but the proton, neutron, the electron are 1/2. They have this intrinsic angular momentum. You can never turn it off. They're always spinning, right? What we're going to find is that this angular momentum, this idea of electron spinning, is not the way we think about it. We think about spinning. Because when we talk about this molecule spinning and rotating, we have this explicit idea kind of conceptually that we have these two heavy masses that have a size and they have a distance between them, and you're spinning it, right? You're rotating it like if this were the moon and the sun, right? Or the sun and the earth. And you have this kind of natural sense of an orbit. But how do you orbit something? How does something spin that has no physical size? Right? The electron is just a point. So how do you spin something that has no size, right? But the fact of the matter is that it has a spin. It has this intrinsic angular momentum, and there's nothing you can do about it. It's always there. Okay, so there's this kind of, what we'll find is that the math dealing with this is very similar to the math as this. They're very similar. They both can be treated using angular ideas. But this is not a classical rotation or angular momentum, as you can think of it, right? There's nothing physical here. There's no mass to spin, but yet it does spin. And so we'll have to talk about that and think about where that comes from. And actually, the answer for that question is somewhat unsatisfying. It's not that it doesn't come from anything. I mean, it sort of does come from something, but we're not really at the ability to explain where this idea of spin comes from. It just is there. It's just something that exists, and it's something that we have to deal with. And we'll see time and time again, chemistry, types of reactions and behaviors and phenomenon in the world that are completely determined and predictable by this kind of weird nebulous idea of spin. Right? Spin drives chemistry. Spin drives bonding. It's one of the most important parts of a molecule is its spin and its interactions of spin. But physically it's a concept that there's no physical analog to. You can't touch an example of it because there's nothing in the macroscopic world that has similar behavior. This is a completely unique property of microscopic matter, right? But luckily we can use the math from our classical case, from our tactile version of angular momentum, to explain how the math of spin works as well, right? Which is nice. At the very least, we have some way to deal with it, even though we don't understand it. We don't understand what it really is. We can't really touch it. So let me just do a quick physics reminder. I kind of skimmed through this last class. We'll look at it a little more carefully. But again, what we're going to be measuring, we're going to be thinking about is the so-called angular momentum, which we write L. It's a vector, at least in physics. And it's equal to the moment of inertia I versus the angular frequency. And we can compare to regular momentum, linear momentum, P, which is m times velocity, mass times velocity, right? And that you can just correlate these directly, right? We have a frequency of velocity, right? This is how many degrees the system subtends in 1 second, right? This is in units of radians per second, if you will. And of course, this is linear momentum. It's just motion, so this is meters per second. And so you can think of this as somewhat of like a mass. Just like we can think of this as a mass. Right? But because we're in a circle, we're not going in a straight line, our definition of mass is slightly different. We have to use a different type of mass. But in terms of physics, they're exactly the same, right? There you have this kind of equivalent mass and some equivalent speed, and that gives you a momentum. Right? It's just this time we're doing it in a circle instead of in a straight line. Okay, and so one thing that we can do immediately is, well, what's the energy of a rotating system? Well, with linear motion, the kinetic energy, this is kinetic of T, is equal to p squared over 2 mass. Okay, so we can take the square of the momentum and divide by 2 times the mass, and we get 1/2 mv squared. You can convince yourself if you square this and divide by 2m, you get 1/2 mv squared, which is kinetic energy. And we can do the same thing here. But we can say that the kinetic energy of angular energy, if you will, kinetic energy, is the momentum squared divided by 2 times the mass. So we can write T equals L squared over 2I, where I is the moment of inertia. Okay, and so in order to determine this, well, we have to measure the angular momentum, right? We have to see how fast it's spinning. But we also have to measure its mass, right? Its inertial mass or its moment of inertia, as we call it. And every object has its own moment of inertia. Let me write that down. Every object has its own moment of inertia. And so it's a matter of being able to calculate the moment of inertia for a given object. And the way that we're going to do it for molecules is we'll treat atoms as point masses with coordinates, call it r, with a vector r, which is x, y, z, with respect to the center of mass, which is at the origin, where the vector for the center of mass is at 0, 0, 0. All right, so what we can do is we can draw this molecule on a coordinate system. Luckily, it's just a line. It's not too hard. We'll just draw a straight line. We'll call it x. Like that, and we'll put the center of mass of our molecule here. And then for HCl, we can just calculate how far chlorine is from the center of mass. Let's say it's right here. Let me make it green. So here's the Cl atom. And then the hydrogen slightly further away because the center of mass is closer to the heavy atom. So maybe the H is here. And then what we can do is we can calculate a distance. If we call the distance from the hydrogen to the center of the mass is R1, and the distance from the center of mass to the chlorine is R2, we can write R equals R1 plus R2. So we can just define a distance, right? This is R, the bond length, if you will, right? That's all that is. It's just a bond length. And of course we have masses, right? So there's a mass of chlorine is about 35, and the mass of hydrogen is 1. And for a linear molecule, or so in general, I is the sum over all of the atoms. From I equals 1 to n atoms of the masses of those atoms times their position squared. Right? It turns out the mass is a little more complicated than that, but basically that's what it is. It's a mass, it's just a sum of the masses times their distance from the center of mass squared. And for a linear molecule, for a diatomic rather, you can simplify this equation so that I for a diatomic is the reduced mass, mu, r squared, where r is the bond length. Mu is going to be the product of the masses divided by the sum of the masses. Okay. So any diatomic has this structure to it where it's the reduced mass times r squared, right? That's the effective rotational mass of our system, right? It's the same idea as normal mass, but now we're spinning it in a circle. We have to represent it differently. And of course, if you think about a great comparison of this, just to convince you that this is meaningful, is imagine that you have an object, or you have, let's say you have two figure skaters, all right, who rotate with the same amount of angular momentum, right? Imagine you spin them up exactly the same amount. You feed in precisely the same amount of energy into them. All right, and one figure skater puts her arms in, and the other one stretches her arms out. And so the angular frequency, so they both have the same L, effectively. But what's happening is their moments of inertia are changing. So again, the figure skater with her arms wide has a large moment of inertia because her R is large, right? The distance from the edges of her body to her center of mass are big because she has to go through her arms. So I is big. So fixed L at a large I, omega is small. So when she opens her arms, she rotates very slowly. But then the figure skater closes her arms. Well, she has the opposite effect. Her R is very small. Her arms are closed. The displacement from the center of mass is quite small. Constant L, her angular frequency is very large. So when we talk about molecules, what we're going to find is that molecules can show quantized values of angular momentum. Basically, they have 1 unit of angular momentum, 2 units of angular momentum, 3 units of angular momentum. Right? So this number, in some ways, can be proportional to a number. And so what that means is that at a given number, at a fixed mass, so if this is always 1 for 2 different molecules, then the frequency at which they oscillate depends on the size of the molecule. So the bigger the molecule is, the lower the energy required to spin it up 1 unit of angular momentum, because I is big, therefore omega is small. And if you have a small molecule, I is small, which means to get 1 unit of angular momentum, omega needs to be big. Okay? And we'll see that in the energy level spacings of rotation. Right? We're going to be able to calculate energy levels, just like we did for the particle in the box, but now it's for rotations. That the spacing between energy levels of rotation gets smaller as the system gets larger, right? Because as I gets big, omega gets small. Okay, so that's really nice. What this means is that if we can measure energy levels of our system, measure changes in energy and rotation, we can actually figure out the structure of the molecule, right? They're directly dependent on the moment of inertia. So if we know something about the spectroscopy or the energies, we can calculate structure. So angular momentum is kind of cool because it's completely dependent on size and shape. Nothing else. Nothing fancier than that. Okay? And so this is all classical though, right? We haven't done any quantum mechanics. We're just talking about two spheres connected with a string, if you will. A rigid string. Okay? But what we want to do is we want to take this theory and now we want to promote it to quantum mechanics, right? We want to create a Hamiltonian, solve for the wave functions, but we'll use these physics as our guide. What we're going to do is we're going to take this molecule and then we're going to promote it to a quantum mechanical system to get quantized energy levels. And we'll end up having some really interesting results. All right, so let's do that. So we already have our energy expression, the kinetic energy. So all we have to do now, let me go ahead and erase this for now, is now calculate a Hamiltonian operator. So just remember that energy operator is the Hamiltonian, which we call H hat. And H hat has two parts, the kinetic energy and the potential energy. Now we know what the kinetic energy looks like. It looks like L squared over 2I. That's nice. We don't really know what the potential energy is, but let's assume that there is no potential energy, right? All we're doing is we're spinning a rigid object. Right? It's just freely spinning. There's no potential, right? There's nothing preventing it from spinning or promoting it from spinning. It's completely free. So for this system, we're just going to set this to 0. You don't even have to worry about it, right? We're going to assume that the body is rigid, right? That R is fixed, and you're just spinning this around the center of mass, right? Free. So Hamiltonian is just kinetic energy. So the Hamiltonian is going to be some operator L squared over the mass, like that. Just all we're doing is we're taking the physics from before and we're just putting hats on top of things, right? And then we need to solve H psi equals E psi. Okay, that's the same thing we did for the particle in the box. Now here's the problem. What does L squared look like? And this turns out to be the difficult problem. Okay. All right, we need to come up with what that operator looks like. Remember with momentum is minus IH times the IH bar times the derivative with respect to position. Right? What does it look like in terms of L? And so that's not all that obvious, but we can figure it out. So let me go over here and we can maybe figure out L squared a little bit. We're going to actually have to use a little bit of vector math here to come up with it. But once we do, we'll actually have quite a few tools. So again, let's think about what L is. L is a vector, or angular momentum is a vector, and it's perpendicular to the axis of rotation. So if it's rotating like this in the plane of the board, excuse me, then the angular momentum vector is sticking out of the board like this. Okay, so let's define some axes. So what I'm going to do, again, this is a three-dimensional system, right? We have 2D, right? The molecule is on the board, 2 dimensions, but we also have an angular momentum pointing in this direction, so it's a 3D system. So what I'm going to do is draw a 3D axis system, X, Y, and then I'm going to do the Z in this direction. Treat the board as the XY plane. Right, so Z is out of the board, if you will. All right, so I'm just rotating things a little bit. Okay, so Z's out of the board here, so I'm just going to rotate it so Z's pointing up. And so we can put our molecule in that space here. Let me draw a different color, sorry. So here's our HCl. Again, it's sitting on the x-axis, if you will. And it's rotating in the xy plane. Whichever, actually, so it needs to go the other way. I apologize. I'll just do this. So it goes this way. We're going counterclockwise. So that the angular momentum of the system is pointing in the z direction. So I'll draw a vector in this direction, which we'll call L. Let's say angular momentum is out that way. And the definition of angular momentum is the distance of the system to cross the product or times the linear momentum. Okay, so you're going to have a displacement vector, which is this, and there's going to be some linear momentum pushing it that way, and it's spinning around its axis, and that causes you to have angular momentum when you take the cross product of those two vectors. Okay, you should automatically maybe even see that we're going to come across a difficulty here because the particle in the box was a one-dimensional system, right? It's just on the line. But here we have to deal with 3 dimensions, right? Which is kind of might be a difficulty. And we're going to have to do a little bit of math to fix that. But let's evaluate. We can now calculate L. Instead, what we should do is talk about the operator as being the cross product of the momentum and the position operators, right? That's how we're going to do quantum mechanics here. So let's calculate that. So L is R cross P which is the determinant of, let me think about this, x, y, z, px, py, pz. We'll call this the x direction, the y direction, and the z direction. It's that determinant. And that's going to be, this is just me trying to bring out my vector math from about 20 years ago. So it's going to be ypz minus zpy x. This is the what this is sorry, let me change these. These are all operators. And this is in the x direction. Maybe we should call these, yeah, we'll just leave it like that for now. And then there's a minus sign for the y, xpx minus zpz, y direction. That's the y component, and then there's a plus, I think it is, xpx minus ypy z. Okay, so these are the three components of the angular momentum vector. And notice that they're products of two operators, the momentum operator and the position operator. So we can let's call these the components of L. So I'll call this one L sub x, this is L sub y, and this is L sub z. All right, and I'm not going to do all the math out, but we will return to it to evaluate these. Remember, oh, I have the colors and stuff, sorry. This is supposed to be red, but it's not. Okay, well, anyway. Recall, yeah, this says red, but it's not giving me red. All right. That the momentum operator in a certain direction is minus IH bar times the derivative in that direction. So Py is also minus IH bar d by dy. And Pz is the same thing, but in the z direction. And so on and so forth. And of course, x, y, and z are just x, y, and z, those operators. So notice that the momentum operator is actually three-dimensional, right? The x component has some information about z and y in it. The y component has some information about x and z in it. And the z component has some x and y information in it. So L, in general, is a three-dimensional vector. Right? It sustains, it can be any place in this three-dimensional system. And what's worse is now we have to take the square of it, right? Because we have to do L squared, right? So L squared is Lx squared plus Ly squared plus Lz squared, like so. And so then we have to take these operators, right, this combination operator, and square it, and then do all the math to figure that out. All right, and so that algebra is pretty complicated. But we can simplify things. Well, I'm just going to skip that math, right? Because in order to calculate L squared, we have to do a lot of algebra, and that's not really worth doing. Rather, the results are interesting. What we end up getting is that h squared, which is L squared over 2I, is proportional to, it's not exactly equal to, something that looks like h bar squared over 2I times a bunch of second derivatives in all three directions. Right? And the reason why you get second derivatives is because you're taking the square of these, right? And you're going to get like a px times a px and a px times a pz and so on and so forth. And so you're going to get a factor of square in there. So we get some second derivatives. But the problem with this is that this is a really bad coordinate system for us. This is describing motion in a sphere using rectangular coordinates. All right, what do you think about? Let me try to explain this on our axis system. Think about let's fix L to have a specific length. Okay? So let's just say, for instance, the length of L is 1. Okay? The length of the vector is 1. Where can L point? Well, L can point in any direction it wants, right? It can point in this way. It can point in this way. It can point along one of the axes, right? And if you think about what the shape looks like of all the possible vectors, it's a sphere with radius 1. Right? This L can point in any direction. Basically, the molecule can rotate in any direction it wants in 3 dimensions, and it's symmetric across all the axes, right? If you cut it halfway this way, it's the same as cutting it halfway this way. Everything's spherically symmetric. So in fact, the motion of L, the motion of angular momentum, and therefore the energy of motion, is something that's spherically symmetric. And it can exist anywhere in this spherical region. Right? So in order to calculate properties of spinning, of angular momentum, we need to account for all 3 dimensions. And the fact of the matter is that it's in a sphere. And because of that, using dx plus dy plus dz, which basically subtends a cube, right? When we add points that are dx, dy, dz, we're building straight lines, right? We're building squares and cubes. And so we're trying to describe behavior that's on a sphere with cubic or rectangular coordinates, and that's just not useful. Right? This is something that exists on a circle, not on a rectangle or a square. And so we really shouldn't use Cartesian coordinates anymore because they're just not useful. Right? This is literally like modeling a sphere with a cube. Okay? It can work. You can make that cube look like a sphere, no problem, but it's not pretty. Right? So there must be a more natural way to define the coordinates so that we can take advantage of the fact that our system exists on a sphere. Now, if you've taken Calc 3, you've probably seen this before and you're dreading it, but we have to move the spherical coordinates. So let's talk about that. So let me go ahead and erase this and let's redraw an axis system real quick. Now let's not worry about our molecule. Let's just think about our vector, L. Here's my x. Here's my y, and here's my z. And let's draw our angular momentum vector in some arbitrary position. Here, it looks good. And then we can define the coordinates of the projections of it by writing L sub x. Right, this is the length of L sub x. This is L sub y. And then if we draw a point here. Let me see if I can do this. That. Sorry, I take that back. This is L sub z. I apologize. And L sub y would be this point right here. It's kind of sticking out of the board. This L is kind of pointing out of the board in this direction towards my head. Okay, and so the question now is that the end point right there, we could write x, y, z. Right? This is where it is, x, y, z. Right? But that's not a very useful number for us, right? Instead, we want to think about, now what we're doing is we're just drawing squares. Right? We're just drawing squares. That's not helpful for us at all when we're dealing with things on a sphere. So we need to convert this into something that's more useful for a vector on a sphere. So I'm going to define 3 new coordinates. The first one I'm going to define is the length of the vector. We'll call that r. Let me give it a different color so it's clear. So instead of measuring x, y, and z, I'm going to measure r, which is the length of the vector. I'm going to measure the angle that it subtends with the z-axis as theta. And I'm going to measure the angle it subtends with the y-axis as gamma, or psi, or phi, rather, phi, like that. Anyway, we can now calculate this position in terms of these three coordinates. And I won't go through the math of this. It's pretty easy. You can just look it up online if you're really interested in it. It's not too hard to do. But the conversion from rectangular, which is x, y, z, to spherical, which is r, theta, phi, okay, is this. R is equal to, again, it's just the length of the vector, which is just x, the square root of x squared plus y squared plus z squared, right? It's just the Pythagorean theorem. The length is the square root of the sum of the squares. Theta is the inverse cosine of z over r. Right? And gamma, or phi, sorry, is the inverse tangent of y over x. Okay, and then we can convert these to x, y, and z just to keep it simple. I'll just give you the formulas to convert between x, y, and z and r, theta, gamma. X is equal to r cosine phi, sorry, I keep calling it gamma, sine theta. Y is equal to r sine phi sine theta. Did I have this fixed? I have this flipped, sorry. I have to go back and check that again. Z is r cosine theta. Just a sec, let me double check that real quick. I have a typo in my notes. I always forget which the order is. So anyway, so the conversion is not too difficult, but it is a little awkward. But even though we're going to make our coordinate system awkward, it will simplify the rest of our math significantly, because now we can communicate about motion on a sphere. Okay, I see the problem. Okay. Oh, I see it. I just can't read. Yeah, this is right. Sorry. So by doing this conversion, right, it's a little awkward, but what we're going to do is when we convert these derivatives at the operator into spherical coordinates, we're going to have a much easier problem to solve. Right? It's going to simplify our math significantly, because now we're going to think about motion on a sphere instead of motion in a box, right, which is much more appropriate for our system. Okay, so these are the conversions between the two coordinate systems. You can look these up they're in calculus books. We won't do many unit conversions in this class. We're not going to be converting between these things, but it's good to know that they exist, and this is how they look, right? What we're going to do is we're basically just going to change our point of view from looking at a box and look at a sphere instead. And of course, that's going to become very helpful for us, because what is the hydrogen atom other than a sphere in some ways, right? You have an electron orbiting around a center point, which is your proton, and you can imagine that it shouldn't be that hard to think about it. The electron, there must be some situation where the electron can be at any angle with respect to the axis system, which just subtends a sphere. If you assume that the distance between the electron and proton is fixed, right? It just builds a sphere, all the possible locations it can be. So moving to a spherical point of view is actually really helpful for us, because it'll make the physics more straightforward, right? Because we're communicating the language of spheres instead of the languages of boxes. Okay, and so unfortunately though, when we convert, we'll come back to these angular minimum operators later. When we convert our Hamiltonian, L squared over 2i, we do all that algebra of all those components, all that algebra, get it all done with, and then convert x, y, and z to these coordinates. You end up getting kind of a nasty looking formula, bless you. Or the Hamiltonian is h bar squared minus h bar squared over 2i. And then the second derivative operator becomes really nasty. I'll write it out. It's 1 over r squared times the derivative with respect to r of r squared times the derivative with respect to r plus 1 over r squared sine theta times the derivative with respect to theta, sine theta d theta, plus 1 over r squared sine squared theta times the second derivative with respect to theta. Or with phi, sorry. Let me write this symbol like I wrote it over there. There we go. Okay, so this looks nasty, right? And unfortunately, talking in spherical language can be somewhat difficult, and it looks difficult in terms of the math. But notice that I've wrote in proportional here that there's some second derivatives, but the actual formula for that in terms of cubic coordinates is much more complicated than this. There's lots of extra terms. The x's and the y's talk to each other. There's some square roots, right? There's some cosines and sines, right? It's a really nasty formula, right? And it turns out by changing the spherical coordinates, we can simplify it quite a bit. This is as good as we can do, though. But remember, we're in 3 dimensions. So that's kind of the way it goes. But we can kind of evaluate this formula and actually realize, and we kind of come to a realization that this looks a lot like this formula. It's just got some extra terms in it. If we look, for instance, this first term, only dependent on r and the derivative, the change in the radius. Right? There's no angular coordinates in that. Notice here, this is only dependent on theta and r. So this angle in the distance, not dependent on this one at all. And this one is dependent on all 3, but just the derivative with respect to phi. All right, so this is in some ways if we look at the formula here, there's 2 factors of the derivative here. So it's kind of like the second derivative of radius. And this is somewhat the second derivative of angle, theta. And if you look here, this is just derivative in terms of phi, or phi. Right? So in fact, the structure of this is very similar. And a rectangular coordinate is proportional to the sum of the 3 second derivatives with respect to the 3 coordinates. And here we have the same thing. We have three terms, each respectively dependent on one of the 3 derivatives. Okay, nothing else. So even though it looks nasty, it's actually not that much more complicated. There's just extra terms. We're never going to have to do any math of this, but I just kind of wanted to show you the complication that's involved, right? That going from 1 dimension to 3 dimensions, we have to deal with multiple variables. The end result of this is now what we're going to have when we solve the Schrodinger equation for this. Is we're going to have a set of wave functions that are dependent on all 4 coordinates. They're dependent on r, theta, and phi. They're going to be 3-dimensional functions. And remember what we do with wave functions. We integrate them, right? So we're going to have to do 3-dimensional integrals to calculate probabilities. Right? We're going to have to take the wave function squared. The wave function is a function of at most 3 variables, 3 coordinates. So therefore, we have to do a triple integral to integrate it. All right? And so that's where this math really comes into handy. This is all just preliminary work for us to be able to come up with an equation or a wave function. But this math will come in super handy when we want to integrate, because we're going to have very simple functions in terms of phi and phi and r, or theta, phi, and r. They're going to be very simple wave functions in terms of those. And then we're going to have to do this very easy, and then the integrals we're going to integrate things that are angular with integrals that are where the angles are built in. Right? So it'll be very natural. Instead of me having to figure out where in a cube the sphere exists, we can just subtend over the cube by integrating over pi, over 2 pi, and then 0 to infinity. I'll write that down, the bounds for these coordinate systems. So let me show you what I mean by that. So r can be anywhere between, right? R can either be 0 to infinity. So r is anywhere between, let me write it like this instead. So r can be any distance, but it can't be negative, of course, right? There's no such thing as a negative length. Theta can run between 0, which is where it's pointing in the z direction, and negative, and then pi, which is where it's pointing z. So theta can only exist between 0 and pi. And then gamma, or phi, can be any angle in a circle, right? Any direction in the xy plane. So phi is either between 0 and 2 pi. Right? And those are all our coordinates, right? So instead of having to integrate from 0 to infinity across x, y, and z to do our integral, we only have to integrate radius to infinity, because the other coordinates are just angles of a sphere, or angles of a circle, and there's only 2 pi of those. So that actually simplifies our math quite a bit. So by moving to a more natural spherical coordinate system, we'll end up, the math that we care about, the integrals and the probabilities, will just be integrals of trigonometric functions, effectively. Trigonometric functions with respect to coordinates that are angles, right? And that should be really easy to do. We're not going to have any x squares and y squares and inverse cosines. We're not going to have any of that nasty junk. We're just going to have sines and cosines and maybe some r's, right, depending on the distances. Okay, so it will simplify our math practically down the line. All right, so we're making our lives hard at the beginning to make our math later on much more simple. Okay, but the one thing that I want to mention is that for our molecular system, right, remember we have a diatomic molecule, but it's rigid. If our molecule is rigid, I'm going to go with a different color. So if our molecule is rigid, we call that a rigid rotor, which means the bond length doesn't change upon rotation. The derivative with respect to r is 0. Right? The bond length, the distance between the atoms isn't changing at all. Right? So for a rigid rotor, this term completely goes away, right? Because it's dependent on d by dr. But it's always 0, because the bond length of the distance between the atoms is never changing. So this term actually goes away, and what that means is that our wave function is only going to be dependent on 2 variables. Well, maybe 2, but it's only dependent on theta and phi. Right? So we can actually simplify this further. So for a rigid rotor, for a rigid molecule, Hamiltonian minus h bar squared over 2I times 1 over sine theta d by d theta sine theta d theta plus 1 over sine squared theta d squared by d phi squared. Like so. Still brutal, but it's simpler. We're getting better. Okay, so when we go to solve the Schrodinger equation, what we want to do is we want to figure out a set of wave functions that when we plug it into here, we just get a number back times the wave function. Okay? There's no obvious answer to this question, right? When we did the particle in the box, I asked you the question, what's a function where you take the second derivative and you get it back? Right? And we came up with sines and cosines. But it's not immediately obvious that that's the answer here, right? Because we've got these factors of sine theta here, right? So if let's apply the Hamiltonian just to get a sense of it, right? If we apply h to psi, what does it look like? It's going to be minus h bar squared over 2I times 1 over sine theta d by d theta times sine theta times the derivative of the wave function with respect to theta plus 1 over sine squared theta times the second derivative of phi with respect to, psi, the wave function with respect to phi squared, like that. Okay, and this is going to be equal to a number, the energy, times psi. Well, that doesn't really help us any. Right? It's still not obvious. We need a function that when you take, it's a two-variable function of theta and phi, that when you take the derivative of it, multiply it by sine, take the derivative again, divide out the sine, and then add this derivative to it, that you get a number back, right? It's not an obvious problem at all. But thankfully, people have thought about this problem a lot. It turns out that this is actually a really common function. In fact, it's this kind of what we call a differential equation, right? We have a function times some set of derivatives of a function and a function. Is actually something that you can solve, and you often solve it in problems. This is something that comes up very commonly in problems where you're dealing with motion on a sphere. For instance, spherical waves. Things that are on anything that's confined to a sphere that has oscillations tends to have solutions that are very similar to this. Well, we can appeal to that knowledge. Right? I'm not going to go and solve that. In fact, the first time I ever saw this solved by hand wasn't until graduate school, right? Even in my undergrad, we just wrote it out and said, well, we can't do this math on our own. Let's appeal to the answer. And the answer is actually really beautiful. Oh, and my knowledge of things are over here. The wave functions for this. So once we solve it, the math comes out beautiful. Like it just simplifies. Everything simplifies out. It's because we've changed to this idea of using a sphere. Right? So we've made all the hard parts in the calculus. And once you go to the solution, when there's solutions in terms of angles, it simplifies out beautifully. Do I have some answers for these? I don't. Okay. All right, the first answer is actually quite useful. First, you get the energies back. So solving the Schrodinger equation for a rigid system, we find that the energy of the system is quantized. The quantum number that we use to talk about rotation or angular minimum is J. We call this the total angular momentum quantum number, J. All right, so anytime I say J, think total angular momentum, is equal to h bar squared over 2I. Again, we see that energy unit again, the mass. Right, that's just kinetic energy. Times J plus 1. Okay, and J can be 0, 1, 2, any positive energy. The system quantizes itself when you solve the Schrodinger equation. You get this beautifully simple structure. The energy levels are spaced by the by roughly proportional to the quantum number squared. Just like we saw with, remember with the particle in the box. Particle in the box which kind of looks like pain in the butt. Particle in the box. The energies are proportional to h squared over 8ml squared n squared. Right? H squared over 2I is our little spectroscopic constant. H squared over, this is just h squared, excuse me, over 8ml squared. Right? That's the same thing as h bar squared over 2I in terms of units, times n squared. But instead of having n squared, we have jj plus 1. Right? So the structure changes slightly. And we can see that instead of being n squared, it's j times j plus 1. But the structure is very similar. Still proportional to a number squared. Okay. And now the question is, what do the wave functions look like? And the wave functions have a special name and a special label. And I'll have to pull up some, I don't remember them all of them off the top of my head. So the wave functions for angular momentum are called the spherical harmonics. And what they are effectively oscillatory functions like sines and cosines, but ones that are defined on a sphere. And sines and cosines are defined on a line, right? They're waves, one-dimensional waves, right? And so the equivalent, just like we came up with momentum, right? We've converted from linear to angular momentum. We're converting oscillatory linear wave functions, right? Oscillating waves on a line or a string, into functions that exist on a sphere. Right? So these are oscillatory functions. They'll be functions of theta and phi, and maybe r as well. Actually, there's no r dependence, excuse me. There'll be functions of theta and phi, and they'll have some oscillatory kind of repeating structure defined over the coordinates, just like sine and cosine. And we give them a special name, or a special logo. So psi j, so if the wave function for the j state, theta phi, is a function of two angles. And we call them the spherical harmonics, which we label y. So big capital Y. And they actually have two quantum numbers, j and m. And they're functions of theta and phi. Okay. So in fact, so there are two quantum numbers. J, which is total angular momentum, and M. And what is M? If you look, it's not the energy is not it's not with respect to energy, right? So in order to define the wave function, you need two indices, right? The spherical harmonics are defined by two numbers, J and M, right? We know what J means, right? The energies depend on J. It's total angular momentum, right? It's the length of L, if you will. It's proportional to the length of the angular momentum vector. But what's M? I'm going to give it a name. It's called the azimuthal quantum number. Of course, we don't know what that means yet, but I'll explain it to you in just a second. Right. Why do we need two? And this turns out to be a very beautiful and kind of strange consequence of quantum mechanics. Why we need two, and why the energy is not dependent on the second one. Let's draw our system on an axis system again. Well, I'm going to draw it x, y, and z. All right, and I'm going to draw my angular momentum vector, some direction, like that. All right, so here's L. Okay, and we know that L squared is equal to j plus 1 h bar. That's for the energy. Sorry, h bar squared, sorry. j plus 1. Which means that L, the length of L, is the square root of j plus 1 h bar. The length of that vector is that length. Right, so the length is dependent on j, right, the total angular momentum. Right, so the more angular momentum you have, the longer your vector is. So what is M? Well, it turns out M if we project the length of the axis of the L on the z axis, so let's build a new vector called L sub z, like that. And the length, it turns out, the length of LZ is m h bar. So m tells you how much of a component of L is on the z-axis. Okay? And M is what determines that. And M, it turns out, can be negative j, from negative j plus 1, negative j plus 2, 0, 1, j minus 1, to j. It can be any number between negative j and j. And what that means is that, what that tells you is something about the direction. Right? Remember that the energy is dependent on L squared. When you square a vector, you lose all of the information about its direction. Right? You don't know anything about its direction. So you can have an L squared that can be pointing in any direction. Right? And L squared will be the same. Right? I can point another vector in this direction with the same length, called this L prime. Maybe it's pointing in this direction, or maybe it's pointing in this direction. L prime prime. Okay. And L squared is the same as L double prime squared and the same as L prime. They all have the same length, right? But they have different directions. Well, what changes between them? Well, they have different L sub z. Right? So for instance, if the vector is here, L sub z is going to be greater than 0. If the vector is along the x or the y plane, if you will, anywhere in the xy plane, L squared again is some value, but Lz is 0, which means m is 0. What if it's negative? Well, if it's negative, then the projection is along the negative axis, and so m is going to be less than 0 there. And for this one, well, this one and this one have the same m effectively if they're pointing in the same direction, if they're perpendicular to each other like that. Then if this is m, then so is this is m as well. Okay. So what it at least tells us is that, so what Lm is the projection of L on the z-axis of the system and it's the quantum number for it, rather. It's the index for the quantization for the projection of L on the z-axis, right? So for instance, if L squared is 1, h bar squared, right? This is jj plus 1. So if j is 1, that's 1 times 2, 2 h bar squared. So if j is 1, L squared is 2 h bar squared. And if what that means is that if m is positive, then that means that L is pointing in some direction, right? That the molecule is rotating. If I were to draw the molecule, right, the molecule is kind of rotating in this direction, like that, around L. Right? Remember, L is perpendicular to the axis of rotation. So if L is pointing in this direction, like this, then the molecule is like this, rotating, okay? Like this with respect to the z-axis. If m is 0, then that means L squared is like this, and the molecule is like rotating on its axis like this. Okay? Now, if m is negative, then that means the projection is z is negative, and it's rotating like this instead. Right? Same as going positive. Right? So if L is pointing in this direction, the molecule is rotating like this. If L is in this direction, the molecule is rotating like this. If m is 0, right? The axis of rotation is like this. Again, I'll do it again. If it's like this, it's going like this. If it's this way, it's rotating this way instead. If it's negative, it's rotating the opposite direction, and so on and so forth, right? So m tells you something about the direction of rotation. Okay? And it turns out those are the only two things we can know about. This completes every piece of information that we can possibly ever know about angular momentum from a single system. In quantum mechanics, you can define a total angular momentum, and you can know the projection along one of the axes, of the 3 axes, but you can't know all 3. Right? We'll be able to show that probably next week. I'll talk about that with spin. But what we're going to find is that this vector, again, if we know the vector, we would know all 3 of its components. But in quantum mechanics, you can only know one of them. You can know the length of it, which is L squared, the length, and you know one of the projections, but you can't know all three. So what that means is, I'm going to draw it one more time. You don't have to draw this, I'm just going to use it as an expression. So let's imagine again, here's z direction, x and y. All right, and let's set our angular minimum vector to be in this direction. Okay, so that means our system is spinning like this around the axis. All right, we can write LZ here. This is LZ. And those are the only two things we know. The only two things we can know. So in fact, what's actually happening in our system is that if we can define these two, angular minimum is completely undefined on the other two axes. So what that means is that in fact the vector doesn't look like one line, but it actually looks like a cone around the z-axis. Because every component on this cone has the same L sub z, but undefined L sub x and L sub y. Right? So in fact, in quantum mechanics, vectors aren't even vectors. They're not even straight lines, but rather they're cones that are subtended by a circle or a ellipsoid, because the axis of the vector, the direction of the vector with respect to the other two axes you don't know, x and y in this case, are completely undefined. So a vector in quantum mechanics is not actually just a line, but it's actually a surface. It's the surface of an entire region that is undefined. All right, we'll be able to prove that. All right, when we talk a little bit more about spin and stuff, we'll come back to this because it's essential for understanding spin. But the take-home point is that in angular minimum, you only get two pieces of information. The direction along a specific axis, which we pick z in this case, right, which is the quantum number m, the azimuthal number, and the total length of the vector, or the total amount of angular minimum. We'll call it magnitude of angular minimum, which is J. It's the only two things we can know. Everything else is undefined about the system. All right, and if in fact, if we decide, okay, well, I want to know what it looks like along this x-axis, we can do that. We can define our system in respect to the x-axis instead of the z-axis, but then you lose all your information about the z-axis. All right, we do for the y, and the same problem exists. The other two axes are completely undefined. Our vector looks like a cone. It doesn't look like a line, it looks like a cone, because we've lost two parts of the direction. All right, and that's intrinsic to the math. We haven't derived it yet, but we will, and it'll become an essential part of understanding this, is that this is the best we can do. We can know the total amount of energy, if you will, the total length of the vector, which is proportional to the energy, L squared, and the direction, roughly. If it's spinning this way, or spinning this way, or spinning this way, that's all we can know. Okay, but that's all we can, nothing else is definable. All right, and we'll be able to show that. So quantum mechanics has the quantum mechanics of the rigid rotor has two numbers that define the state. But for energy, we only need to worry about the length, right? L squared. Remember that E is equal to L squared over 2I. So this is proportional to the length of the angular minimum vector of the total energy. Total angular minimum, how fast it's spinning. And it's proportional to this number J. It turns out that regardless of the direction that it's pointing, it's the same rotation, right? The only difference between a molecule rotating like this and rotating like this or rotating like this is just a rotation, right? You can think of this rotation exactly the same as this one, you're just looking at it in a funky way. Right? I can so if my system's rotating like this, it's the same as taking my entire axis system and rotating it like this. Right? And what I'm doing is I'm changing m by rotating the system from here to here. That doesn't change anything. I've just basically tilted my head sideways. And so they don't actually affect the energy. Okay, but you have to specify it because we fixed an axis, right? We fixed z to be in this direction, if you will. So we have to, the wave function is dependent on the direction of the vector with respect to the axis, which is m, but the energy is not. All right, the energy is only dependent on the length, not the direction. So let me pull up real quick. How much time do I got left? Let's see, 3:30. Oh, we're almost done. Okay, great. Yeah, I just want to write down a couple of spherical harmonics just to show you what they look like. Because I don't remember them off the top of my head. I used to a long time ago. I used to know at least the first couple, but I don't anymore. And I'll draw some pictures of them too for you. Actually, maybe I have them up on Canvas. Let me pull them up real quick. Let me pull them up. Where are they? I know they've got set somewhere. Oh, okay, here they are. All right, let me erase them, and I'll just write a few down for you. So here's the cool thing about, another thing that we can notice about angular minimum that's different than the particle in the box is that the wave function is defined at j equals 0. Remember that in the particle in the box when you set n equals 0, there's no wave function. Wave function is 0 because it's dependent on n. But as we'll find, in fact, you can have a system that has 0 angular momentum, right? J equals 0. It's not spinning at all, and that's perfectly valid. Remember when we were talking about the Bohr model of the hydrogen atom, I said that Bohr predicted that the angular momentum of the electron in the ground state of hydrogen, the 1s orbital, has angular momentum h, bar. It has unit 1, effectively. One unit of angular momentum. And that's the lowest energy level. But in fact, the lowest energy level for rotation, or for angular momentum, is 0, which is what he didn't predict. So we've already corrected his problem. We've already been able to predict that J is defined at 0, which means the system's not spinning at all. What Bohr predicted is that it's always spinning, which is not true. So I'll write a couple here. So if we let m equals 0, j equals 0, the wave function, so I'll call it y 0, 0, theta phi, is super easy, super easy. I think it's 1 over the square root of 4 pi. Yep, it's just a number. That's it. As we'll show, we can integrate this. If we integrate it over the sphere and square it, you get 1, just like you expect, right? Remember, we're going to take this as the wave function, we square it and integrate over all space, which is the sphere, we'll get 1. All right, it's just a circle, right? And so if I were to draw this wave function, or psi squared, with respect to the axes, it's pretty easy to imagine what this looks like. It's just a sphere. Right, what that means is that means that the system equally samples all orientations. All right, so when a molecule is not spinning, its wave function is a sphere. It just looks like a sphere. Right? And what you can think of is that the molecule, if you think about the molecule's orientation in space, it can be in any orientation possible. Right? It can be like this, it can be like this, it can be like this, and they're all equal. Right? And so that means your wave function, your psi squared, just looks like a sphere because you have equal probability everywhere. Right? This might look a lot like the 1s orbital. In fact, it is the 1s orbital. And there's a reason why the 1s orbital is a sphere, because the 1s orbital looks like this. It's a fixed number. There's a little extra complication with the hydrogen atom, but the angular part of the wave function for the hydrogen 1s orbital is just this number. It's just a sphere. The electron can be at any position it wants. You can sample all the positions around the nucleus equally in a sphere. Hence this structure. All right, then for j equals 1, there are 3. M equals -1. Remember that and we'll formalize this a little later, but m can be anywhere between minus j and plus j. So there are three of them, minus 1, 0, and plus 1. And let me just make sure I know these values off the top of my head. Oh, sorry, there's two. Well, there's technically, there's two. They're plus or minus. So, and it is, I always forget the normalization constant. Okay. So this one is square root of 3 over 4 pi. I think it's cosine phi, cosine theta. Yeah, cosine theta. Theta. And these are, I think it's 3 over 8 pi. 3 over, yeah, minus 3 over 8 pi. Sine theta e to the I phi. There's a complex component in there. And then the other one is the sine flip, I think. It's plus 3 over 8 pi sine theta e to the minus I phi. You've seen these before. I'm going to draw them for you. Do these look any familiar to you? You've seen these in chemistry before? Anyone recognize these? These are the p orbitals. They have these lobe-like structures. Like the p orbitals of the hydrogen atom, or p orbitals of the carbon, right? The sp3 pi hybrid orbitals, right? You've seen these symbols. You've seen these shapes before, right? Spheres and lobes, right? These structures are due to the fact that these structures, the orbital shapes that you know and love, or maybe you fear, I don't know the way you want to talk about it, but these structures arise from movement. Right? The fact that the electron can be in spherical orbitals or p orbitals is entirely dependent on the fact that they rotate around a nucleus in the center. And the physics of that rotation is exactly the same physics of rotating a molecule. Except with a molecule, what we're measuring is the probability of the molecules being in a certain orientation, right? The molecule, for instance, in this orbital is going to be along the xz axis, but never along the xy axis. It's always kind of in that region. Or here it can be in any orientation, right? But that's no different than the electron over the proton, right? Instead, we're dealing with an electron orbiting a fixed nucleus, but the math is exactly the same. You form s orbitals for its position. You form p orbitals for its position. As you go up to the next energy level, you get d orbitals. Right? The d orbitals for J3 look like this. And I forgot the other one. There's another one too. There's 5 of them. These are just the d orbitals for electron. Right? These structures appear over and over again. Anytime that you spin something in quantum mechanics, anything, a molecule, an atom, a spin, an electron, whatever, you end up getting this quantized structure where you only know 2 things: the total energy, which is the length of the vector, and the direction with respect to a single axis. And just this knowledge allows you to generate these different combinations. And depending on how much angular minimum, you have different structures, different probabilities. And these probabilities are just the probabilities of the hydrogen atom. The same exact functions. we use we're going to see these spherical harmonics. They're part of the solution to the hydrogen atom. We're going to see them time and time again. And so the theory of angular minimum is shared amongst every object. And they all have these lovely harmonic structures, these orbitals, the p orbitals, the s orbitals, and the d orbitals. Okay? We're just orbiting, we're just spinning something else instead of an electron. But the math is exactly the same as the hydrogen atom. Okay? All right, so what I'm going to do on Wednesday, we'll finish up this a little bit. We'll do some calculations, some practical kind of stuff of the angular minimum, talk about molecules a bit, and that'll put us in a good place to really start tackling the hydrogen atom and the idea of spin, which we'll do next week. So we should hopefully, homework's due at the end of the week. Tomorrow I'm going to do Sean's office hours. For those interested, I will be the one doing them after class for 2 hours because he's out of town. And homework's due at the end of the week, and I'll have a new problem set for you next week. Have a good day. You too, thank you. Hey, thank you.